Welcome to the Aurorasaurus Ambassadors call for November 2024. I'm so pleased that so many folks could join us today, and we are going to have a great discussion here with Dr. Mike Henderson from Los Alamos National Lab and their group there that studies the space environment. And Mike is an expert on many different auroral types and the particle populations out in space that correspond to them. And he has a great recent paper on how many different kind of unusual types of aurora relate to each other, relate to substorms. He's going to tell us all about that today. And we're going to have a little, maybe more conversation if you're okay with kind of questions or interruptions and that sort of thing, Mike. Um,
Sure, yep. Good.
yeah, thank you so much. And we'll try and define terms too. So I don't know, you could start with your with your title here, but mesoscale is one term. It has a definition. I couldn't quote you the definition right now there. I think most people here probably know many of these terms, but I think you will get to defining them as well as you go. But yeah, please keep that in mind. And then this was a talk that we've been waiting on for a little while from last year's AGU, but it's very appropriate here. Yeah, mesoscale is like a Goldilocks zone. Yeah. But I'll turn it over to you. Thank you so much, Mike.
Okay, great. Yeah, so sorry for the long title, but it sort of describes everything I'm going to talk about. So, yeah, as Liz was saying, there's a lot of different types of aurora that people know about and have studied from space and the ground for years. And it's kind of really only in the last, maybe decade or so that a lot of these things have been starting to be linked up with each other. So I'm going to go over probably what most of these things, I might skip over some of the particle stuff because it might take a little bit too long to explain some of the plots in there. But for all of the auroral stuff, I'll try and explain in more detail. So this is an outline. I don't know if people are familiar with all of these terms, but a lot of these things are relating. These terms are relating to the types of auroral features that we see a lot in global auroral imaging and also in, say, the Themis all-sky imager arrays. So there's these auroral streamers, which I'll show what those are. There's things called auroral torches, omega bands, and then some of these things can lead into or be commingled with new substorm onsets. And then there's some really interesting things called giant undulations, or GUs, people call them. I've also seen in the literature people referring to these things as sawtooth aurora, although that's kind of a bad name because we already have something else that we call sawtooth events. But you might see that in some papers, people referring to these giant undulations as sawtooth auroras. And then there's these really interesting things called detaching arcs or detaching SAR arcs. And that kind of is a bit reminiscent of things like Steve, at least what people used to think Steve were, and maybe they still are. Anyway, based on a lot of these observations, we kind of came up with a unified model that might explain a lot of these different things happening and where they happen, the times that they happened, and so on. And so then I want to show some ground-based time-lapse sequences that somebody from New Zealand got, showing that you can get some of these things happening together, which was kind of a surprise. And I think it's really exciting that, maybe it's kind of giving some credibility to the model that we proposed. And like I said, maybe some of this particle data I won't go into too much detail on, but it's interesting too. So this, by the way, this is a AGU talk. So at the AGU, you have like maybe, between 7 and 10 minutes to give all of this stuff. So I went a lot quicker at AGU than I am now. But anyway, so I don't know if people have seen this kind of a display of the aurora. So this is actually a movie of the aurora taken in the green line. Now this is false color, so really it's just grayscale, but I've just used a green color table. But it does have a 5577 filter on it, so it's kind of the green aurora that you would see in the sky. And so this shows some really interesting things. You can kind of see, let me see if I can get a laser pointer up here. Yeah, so this is a visible light imager that flew in the early to mid 1990s and even beyond that, mid to late 1990s and into the early 2000s. And so what you're seeing here is basically the night side in the northern hemisphere. And this is the auroral oval, and it kind of is cut off. This is a visible light imager, so they're really only kind of wanting to look at the night side. The day side would kind of saturate the imager. But what you're seeing here is a lot of these kind of dynamic mesoscale features. Now, mesoscale are features that, you know, aren't the little microscopic things that you need a telescope to see from the ground, and they also aren't like the giant, you know, scale size of the entire oval, the auroral oval. They're medium scale size things, and you can kind of see one interesting thing is you can kind of see these things shooting equatorward from this active poleward arc system here, these auroral arcs, and that kind of repeats throughout this sequence. You can see these things really raining down from high latitudes to low latitudes. And when they kind of break away from the top, so these are streamers, these are auroral streamers. And so you may have noticed these in, you know, when you're looking at the aurora, you might see features coming down more in a north-south kind of direction, coming at you from the north, if you're in the north, south if you're in the south. And so I've kind of made a schematic figure up here that kind of illustrates how these things work. This is kind of now showing, say, the full auroral oval. You can see these features start out here and they come down equatorward. They kind of detach from the top, and then they kind of, you know, slam down into the equatorward region and produce what we call torches. So this is an auroral torch. And then, you know, when you get multiple of these things happening, they can kind of, you know, they can kind of assemble into this train of wave-like features that are called omega bands. And they're called omega bands because they kind of look like, in this figure anyway, they kind of look like an upside down capital omega is sort of how people refer to it. And these things, while they're coming down, especially when they get down to the more equatorward region, they're drifting off towards the east here. And then you can see a bunch of other things in this thing. You can kind of see, commingled with all of this stuff, there's more of an explosive brightening that is a new substorm, and that probably happens right about there. So that was a new auroral substorm. And so what you would notice there is a very, very active aurora in the sky, and then probably everything kind of seeming to go poleward, but then also after that, things coming back equatorward in the form of these streamers and torches and things like that. So these we've known about for quite a long time. I did actually my PhD thesis on these things that we call streamers. And so that was actually from a satellite that was actually launched in 1986. I didn't actually start looking at a lot of that stuff until the early 90s, but so I studied the auroral streamers from a space-based instrument that Canada put up with Sweden. And so that was kind of one of the first space-based imagers that took snapshot-style images. So the tradition up to that point was kind of like these scanned images where you kind of just scanned out the aurora as you flew over it. So anyway, that was, we learned a lot about the auroral streamers from space-based imaging like that. But the connection between the streamers and these so-called torches, and especially the omega bands, we didn't really fully understand until the polar spacecraft launched, and that's what this image is from the polar spacecraft, and there's like thousands of these kind of images that we see from space. And so we kind of made these cartoons. You know, I don't know if you've seen the kind of Akasofu type cartoon pictures of auroral substorms and so on. So, you know, we kind of like drawing these cartoon things to illustrate how this all works. So yeah, these auroral streamers, these mesoscale structures that we call streamers, can evolve into these torch and omega band forms. And so that's pretty interesting. It tells us a lot about what's happening in the magnetotail. And so one of the things that we think happens is that you get kind of bursts of flow in the magnetosphere that are being jetted towards the Earth, and the image of that in the ionosphere, in the upper atmosphere, is these streamer structures. And so it's only been about 20 years or so that we've kind of also been able to connect those with these omega bands. So then another thing that's really interesting are these so-called giant undulation events. And originally they were discovered in DMSP. DMSP stands for Defense Meteorological Satellite Program. So it was kind of like a military weather satellite. And this black and white image here is an example of the kind of thing that you get from that satellite. And the way it works is as you go over the poles, it basically just scans line by line and assembles an image. You don't see a whole lot of dynamics, well, any really at all. I mean, the image can change, the aurora can change in the time scale that it takes to make the image. But this is how we discovered these very interesting wave-like features on the equatorward edge of the aurora were mainly discovered using this kind of imagery. And what I've done here is this is actually taken at roughly the same time as this background image. This is also a NASA polar image. And I've just kind of pasted this on to roughly the same place where it imaged it. So here you can kind of see the giant oval here. You can see the sunlit part of the Earth. You can see these auroral streamer structures coming down, and you know, these are the kind of things that form these omega bands. But now you can also see these giant undulations in this region. And so we didn't know a whole lot about these until we started being able to image them from space. And so this was another example from polar, which kind of shows, again, you see this is very complicated event. This was taken during a storm in 1998. And again, you can kind of see these streamer-like structures coming down and producing these torches. This is kind of a great example of why they were called torches. I think Akasofu coined that name, the torch. And they're just kind of like these really elongated north-south tongues of luminosity that kind of stick poleward out of the equatorward region. Back when Akasofu coined the term, I think he thought these things actually grew out of the equatorward region and went poleward. But you know, now we know that they kind of formed the other way. They actually come from the north and then evolved into these omega bands. Here's a more classic example of an omega band here. But what's interesting now is we can actually kind of start to see a connection now between intervals of when a lot of this kind of intense streamer activity occurs, creating these omega bands, now together with interesting features in this region where we also see giant undulations. And this is actually kind of an extreme event where you kind of saw almost an explosive brightening of this region, and then you kind of see structured, also you would call this mesoscale structuring, you know, not really microscopic, but not very global either. So something happened that produced this, and then it's kind of difficult to see. Maybe this image here, you can start to see just this tiny little spur of of luminosity that's kind of maybe becoming detached. If you zoomed in on that image, you'd probably see this was slightly detached. And so this was kind of one of the first ones that I'd seen that was doing these kind of funny things that I thought might be related to the generation of giant undulations.
And Mike, can you
But
go back for one sec?
yep, yep,
Yeah, so I just wanted to kind of say like, so the first 8 images on the top there, those are showing the aurora brightening over, 20 minutes. And you've got a really great, labeled kind of all these different features. And um,
yeah,
the perspective of the satellite here is looking at, the whole auroral night side. And so, kind of thinking about somebody might be observing giant undulations on the ground earlier in the night, right? That's
yep,
um,
yep,
the side that those are on. While on the other side of the oval, other things are happening as well. So it's also kind of really interesting to see the difference in perspective, looking from above compared to what many folks are, very familiar with, looking from the ground and from part of the whole oval too. So um, are these
yep,
storm
yeah.
events? This one, or is this like a substorm that was strong or
This is a storm. I mean, I guess you would probably call this substorm-like activity, but very, very intense. You get this similar kind of stuff during more isolated, transient kind of substorms as well. But sometimes the magnetosphere gets into a mode where it just keeps doing this kind of stuff for hours, and that was probably the case during this event. But yeah, Liz is right. If you're actually going out to the aurora, there's with an event like this, there's some really interesting things. If you're over so midnight in here is probably like here. So if you're in the post midnight, you'll see hopefully a lot of these kind of torch-like omega band structures, and you have to be at somewhat higher latitude to see those. If you're pre-midnight, you probably have a much better chance of seeing, these giant undulations in Steve, especially if you're actually below where the aurora is looking poleward towards it. So yeah, and it would be really cool to actually see from the ground. I mean, we kind of do now from some of the Themis observations, but those aren't necessarily as high resolution as we maybe want. And I'll show you an example later on what you can really see with high resolution imaging. And I guess the other thing to note here is that, yeah, the top 8 images are in the 5577, so that's the green line. These are, again, just false color images, and I didn't make them sort of the representative colors. So the top 8 are like the green line, and the bottom ones are sort of more of a bluish purple line, the 3914 emission, which is another one that Polar sees. So Polar can see the green line, a blue line, and a red line. The red line is usually not very good. It's kind of blurry and not very. I will have some examples later of
yeah,
that, but
it wasn't bright enough to get as good of images, is kind of what you're saying?
yeah, yeah,
Possible.
yeah,
Um,
and the red line is usually more smeared out anyway, just
yeah.
because the lifetime of the emission is like 100 seconds or something like that.
And in terms of the camera, those are taking images. Are these all the images that were taken? Like it didn't take a 3-minute image, did it? Or it took a one
No,
image and like, yeah.
I think it took, I can't remember what the exposure time for these images were, but it was a CCD, and so everything was exposed at once. These may have been on the order of 10, 12 seconds, maybe something, 6 seconds, I don't know, something like that. I'd have to look that up.
Okay.
The Viking ones that I did my thesis on, they were taken with 1 second exposures. But these from space-based imaging, I think the Polar this is the visible light imager on Polar. I think this is probably as high a resolution as we've achieved from space with dynamic imaging like this. The DMSP that scans out an image as you cross over gives you much higher spatial resolution, but you don't see any time dependence. So I think this is still kind of like, you know, the pinnacle of what we've done from space.
Yeah.
And so then in connecting this now up to some more stuff, so, you know, I'd seen some of these things, and, you know, after all of the discovery of Steve and all of this kind of stuff, I went back to see if we could see anything that we might be able to say, hey, you know, look, there's Steve in these kind of images. And this is an example from January 13th, 1999, where, and again, this is the green line. So now you can kind of see the same sort of, well, actually in this one, you can actually see the limb of the Earth as well, which is kind of cool. You can see, you know, just how big the Earth is, and there's the auroral oval. And again, we're only kind of focusing on the dark part of the Earth because this is a visible light imager. You would just be saturated if you'd looked at the day side. But here you can see a lot of this white stuff in here. These are, and it's a bit saturated here because I wanted to bring out the feature in that you can see later. These are the streamers that are coming down, just like in that previous movie. And they're actually pretty intense here. And I think I have a movie maybe in the backup slides if people want to see that. But in response to this kind of thing, what ends up happening is we start to see in this frame here, you start to see this arc-like feature detaching away from the oval. So it moves equatorward. And so, yeah, I thought this was really cool. And maybe, you know, nobody'd ever actually seen this from these big imagers like this, or the large scale imaging, like either from space or Themis or whatever. But it turns out that people had seen these from the ground, and they called them detaching SAR arcs or detaching arcs. And mainly people from Japan, Shiakawa was one that looked at this, and it has a few papers on this. Now, this is green line emissions. And so, you know, I thought, well, maybe this is Steve. And but you know, we kind of know that Steve is more of a continuum emission. It isn't just in the green or the, you know, the various, you know, favorite wavelengths that we like to look at. So fortunately, you actually do see this. So this is now the red line for this same event. And I think they took fewer red lines, so the time between these are a bit longer. But it's actually kind of a little bit more dramatic in the sense that you can really see this thing separating away equatorward. And this image over here, by the way, is the 3914. And I probably won't have too much time to get into the details of what the significance of some of these different emissions are, but this is kind of an interesting one to look at because it might indicate that maybe there is precipitation, particle precipitation in here, but it's not clear. At any rate, this red line thing really does look like this is generating what somebody would call a SAR arc. And so it's kind of funny that we're sort of coming full circle back to what people thought Steve was before a SAR arc. Now, I don't know if this is Steve because we only have these three wavelengths. So we don't have anything in between, so we can't really tell whether there's continuum emission going on here. If it was a
on the
continuum,
ground and global
exactly,
imagers. Yay. Okay.
yes. And so again here too, it's like, you know, and I've seen this on, you know, maybe there's some other, yeah, I've got some in the backup slides too. We've seen this now maybe half a dozen times from these global imagers, and the separation of these arcs, the kind of detaching away, seems to always come after you have this really intense bout of the streamer activity preceding it. And so the idea that we came up with, it's maybe a bit difficult to maybe understand how this stuff looks in the magnetosphere. But say this feature here is a streamer. In the magnetosphere, you know, which is way out here, something is moving in, and really along the magnetic field lines, it's mapping to this bright auroral feature. When it comes close to the Earth, what ends up happening is that flow in the magnetosphere ends up turning around the Earth, and in the ionosphere, this will look like a rotation like this underneath the aurora. And so when you get a lot of these streamers slamming down into the equatorward part of the oval, really what's happening is the flows are kind of being deflected around this way, well, and the other way if you go the other way, farther over to the east. But in this sort of pre-midnight region where you see these detaching star arcs and where you see Steves happen as well, these kind of flow signatures, the flows kind of move around this way. And so one idea is, well, maybe these detaching regions here have something to do with the same mechanism that the Steve is formed by, and also the giant undulations. And so we came up with a model that, and probably don't have too much time to go through this either, but this is just a picture of the sketch of the magnetosphere looking down on the Earth. And the green region here is a region of really dense plasma that forms close to the Earth called the plasmasphere. And then, and so what's really interesting about this region is it's sort of contained by this teardrop region where everything inside just co-rotates around the Earth. And so what happens is you get plasma coming up from outflowing from the Earth's ionosphere. It falls into this region along the magnetic field lines, and it just doesn't have anywhere to go, and it just keeps accumulating. And it builds up a big density. So that's why you get this dense plasmasphere region. And then outside of that region, anything that comes out of the ionosphere still comes out into the magnetosphere, but it follows these drift paths that kind of take it out to the magnetopause, and they can just be lost. So in the magnetosphere, you basically have this region where you have very dense plasma and very low density plasma. And so we had this idea that, okay, well, you can form maybe these wave-like features on the surface of this teardrop plasma region. And so that's kind of shown here. And so we thought, okay, well, that could, and that is one of the leading explanations for how you can get giant undulations to form in the equatorward edge of the aurora. You kind of have to see how this maps to the aurora. Things that are farther out map more poleward, things that are closer in map more equatorward. So these kind of features would map up into the equatorward region of the auroral oval. Well, so we kind of tried to extend this model by saying, well, maybe if you had a really, really strong flow, that you could kind of break these wave things off, just like waves in the ocean. You know, you breaking waves, you know, waves crashing on the beach or whatever. And if you manage to do that, you could kind of separate some of these tongues of dense plasma. You could break them off, and maybe they could, you know, get entrained into this open region, which could explain some other observations we've had a tough time figuring out. But in addition, you could entrain some hotter plasma from the plasma sheet into the green region, the high density plasma region. And so this whole process too is associated with a lot of shear flow, which is one of the mechanisms that's also thought to cause Steve. And so we've kind of got sort of a hypothetical situation here where, yeah, maybe you get giant undulations, you can get sort of patchy, blobby forms that are moving in towards a region that might represent Steve. And so it's a very cartoon-like model, you know, and we've been trying to model this with numerical models, haven't quite got there yet. But what's really interesting, though, is that we've actually seen some observations that might confirm that this is happening. And so this I found on Facebook, this is a really, really cool time lapse. See if I can get it to run. Oop, nope. Do I have to get out of the laser? Nope. So this movie, let me see. Oh, there we go. Okay, so this was a movie that was taken from a really neat place in New Zealand looking south. And so what you can see here are these giant undulations that happen. So this was a movie taken by Anne Gutschlag. She sent me the movie and a bunch of images and stuff like that over Facebook. But what's really cool about this image is like it's got to be the highest resolution examples of these giant undulations that I've ever seen. And it also shows the images are probably separated by about 10 seconds each. And what's really neat is you can see kind of a lot of elements that might be consistent with the model that we propose. So you see the giant undulations form. You see Steve emissions. So, you know, unfortunately, or fortunately, actually, she saw Steve develop to the edges and kind of move the camera around, which was kind of good. And yeah, so what we're interpreting this to be is, you know, when you actually look, say, this way, well, that's looking to the left. You can see a Steve emission here. And she also panned over to the other direction, and you can kind of see Steve emissions over here. And so what we're thinking is that this whole region that she's kind of imaging in this part here is you're kind of looking through a Steve that's very longitudinally elongated, you know, very much like the kind of detached regions that we're seeing out of the global imaging. But what's really cool is you can actually see there's a lot of really interesting things in here, but so if you go right back to the beginning, first of all, you can kind of see how these giant undulations are really not just simple waves, but they kind of, you know, flop around as they're moving, and you can kind of see little gullies of things in there that may represent some plasma instabilities and things. But you can also see this faint glow of these striations that seem to follow the peaks of these things, and you know, so we're thinking these things are actually, you're kind of looking at a Steve emission, but through it rather than along it, like you would maybe to see it very brightly. But in addition, as this thing develops, you can kind of see sort of blobby green parts coming equatorward as well. And so we didn't see, maybe you weren't in a good position to see the picket fence for this, the green picket fence. But so one idea that we've got, I mean, you can kind of see now that this green is sort of detaching away from this. If it's attached over here, I don't know, but it would have been a really nice thing to be able to see this from multiple viewpoints and maybe at a higher time resolution as well. Because then we'd be able to say, you know, whether some of these regions were really detaching away from the poleward regions. So anyway, this was kind of the first case that I'd ever seen where you really saw this definitively co-mixing of all of these kind of features, like the giant undulations together with a Steve. And so these are just some stills from that time lapse.
I think that's a great example and challenge, perhaps. That's what I heard is like, this is the best one I've seen so far yet.
Yep.
Yeah.
Yeah, and like this is what we see from space, right? So now you really have to stretch your imagination to see similar things, right? So maybe there's giant undulations in a detached arc here. This is another example, two examples here. So this is 1997, and so you can kind of see giant undulations in here and maybe a detached arc here. But again, from these, we can't tell whether these are really Steve emissions. it's easy from the ground, but and with the cameras people have nowadays. This is another example showing development of undulations, but it's not really clear whether there's any Steve-like thing. So sometimes you see one, sometimes you see the other, sometimes you see both. Most of the time you don't see anything.
Mike,
Anyway, maybe I'll.
do you think there's a reason, like you're associating giant undulations and Steve, you're not as much associating giant undulations and SAR arcs? Is that deliberate,
Right.
or could there still be? I mean, there are some observations people are starting to make of both SAR arcs and Steve, and
Yep.
so potentially there could be
Yeah.
star arcs and or giant undulations, I wonder. But
Yeah. So I mean, people I think now are showing that Steve can morph into a SAR arc and vice versa. If I'm remembering some of the talks I saw at last Jam. But that's really interesting because, we have certain ideas about how SAR arcs are formed, and they don't really mesh very well with how we think Steve is formed. So there's still kind of a big mystery about how, well, certainly there's still a big mystery about how SAR arcs initially form. A lot of times when people have looked at these in the past, they look at mid-latitudes, low latitudes, and you see these very stable, that's what a SAR arc is, stable auroral red. You see these things lasting for hours or whatever. But, until recently, a lot of people hadn't really reported how they actually form. And so maybe they form the same way as Steve and they just evolve. Maybe a Steve evolves into a SAR arc. I don't think we know the answer to that.
yeah, I mean, I think
But
the flows of the SAR arcs are less strong, but also wider. And so they could be in the same region and related in some ways. But yeah.
yeah, so this is a figure that I kind of modified a little bit from the AGU one to kind of summarize where a lot of these different things are happening. The colors are not the color of the aurora; they're just to differentiate the different features. So, this is looking down. Midnight is on the bottom. Sun is to the top. Dusk and dawn. And so these blue things are meant to be like the streamers evolving into torches and omega bands. You can kind of see these things turning around here and causing these flows at the lower latitudes. And it's thought that those things drive, kind of like, wind over water waves is sort of the thinking that can generate these wave-like features here. But then we're kind of seeing Steve-like things like this here, or maybe this, that might be related to this region. And so maybe the Steve is due to intense shear flow that happens in the lower part of this region, and that in this region, it's just producing the giant undulations. And so this is all completely unknown. We don't have enough data to understand if this picture is right. Certainly the time lapse from New Zealand kind of looks like this, but then what the underlying mechanism is, well, maybe it's all just a shear, and the Steve represents maybe the equatorward-most region of it. I don't know. There's also these observations where you can kind of see little spur-like features detaching away. Are those the Steve emissions? So we don't really know. And I think what we would really learn a lot from is if we could actually see these kind of things imaged dynamically at both high time resolution and high spatial resolution. Because, from space, we just don't have either one of those. And we don't have the continuum. So we, unfortunately, people, thought if you just imaged the green line and the red line and the blue line, you'd have everything from space. And unfortunately, they didn't foresee the continuum emission in Steve.
Yeah, yeah,
So,
for
anyway,
sure.
so
Um,
that was what I basically presented at AGU, and I have some movies of these things if people are interested.
That's great. Thank you so much, Mike. Yeah, should we see the movies? There's also some great examples of giant undulations from Manitoba in the chat as well. So we can have Donna speak
Ah,
to those and they might, um, you know. Hmm. What is this movie?
so
This
I
is the one
can't
we've
remember.
already
This is,
talked
oh, this
about.
is the January 13th, 1999 event. And so this is kind of showing all the images they had in the green line emissions. And of course, the satellite is moving around in an ellipse, so you're kind of getting closer and farther away. But right there, you can kind of see the separation of that feature. So things are disturbed, but not all hell breaking loose here until now you start seeing a lot of these streamer type things in there, and that's when you see this feature breaking away. I think we went back to the beginning there. Yeah, so in that kind of region like there, but this doesn't have a high enough resolution to really see its actual width. It's only a few pixels wide, so this is where augmenting these kind of movies with high resolution ground imaging would be really important. This imager is dead now. It died in 2008, I think. But the Themis ASI and the T-Rex array can give you some things that look like these on
If it's
days when there's
clear
no
across
clouds across
Canada.
Canada. Yeah, exactly, which doesn't happen very often.
Hmm.
Yep. So yeah, I think there's a bunch of movies. I sent this file, and this file is available to anyone if you want to just look at some of these movies to see what we're talking about.
Yeah, awesome. We can put out the call for Steve images from 1997 through 99. Actually, I mean, one of the folks who's not on the call today, but has a compiled list of Steve images that is very extensive and does include several pre 2015, but we could check with Michael
Um,
Hunnekal. Oh, you have more stuff here.
right.
Did you want to
Yeah.
keep going? Yeah.
No, I mean so this was just a whole bunch of those images of the DMSP overflight showing for that same event that Anne Goochlag took in New
Mhm.
Zealand. And so, yeah, it's maybe a bit small, but you can kind of see New Zealand is down here. You can see examples of these giant undulations in here. So, unfortunately, without any decent imagers in space, we kind of have to resort to these line scanned images, which isn't ideal. Anyway, yeah, so if people have questions,
Yeah, no, there's definitely interest, I think, in well, people here on this call and others are also looking at the DMSP images and comparing to what they see as well. So you do have some kind of good analysis with those in that slide right there. But um, perhaps we can have time for a few people to share and then
sure,
share some of their photos. And then I think there is desire to go back to your teardrop slide and talk through it just a little bit more as well. But
sure, yeah.
Donna, are you able to say something about your images, or would you be able to share them real quick?
I have a video up here. I did share a few images in the chat of giant undulations, and November 11th, 12th, or 12th, 13th last year, I got out really early and I caught undulations um, and there were dunes at the same time. And it was quite
Hmm.
fascinating. There was blobs, and I can't even remember anymore if there was a SAR at that time, but I'm just loading up that video, but I could share my screen and play it if you like.
So it'd be interesting also to calibrate the language that you guys are using. Like I think Anne Goochlag called these things blobbies or something. I can't remember, or ectoplasm, from the, Ghostbusters or something. And I would imagine that's what they would look like. But yeah, so if people had sort of a language that, we could find out when they were imaging things that, what we're calling them, what they're calling them, we could get on the same page.
Yeah, I
Like
think
you'd
giant
mentioned these
undulations
blob things.
are becoming a more well-known term. I don't know, Margaret, if that's a well-known term in the that you all use in the Southern Hemisphere as well. That would be a question for you.
Sorry, giant undulations is very well known here. Yeah. Sorry, as we're referring to
Yep.
something else. I was actually trying to figure out how I was going to be able to screen share at the same time. So, have I answered that?
Yeah. And Donna, if you're sharing, I'm not seeing anything, or you're trying to share also.
Oh, okay, sorry.
No, well, you might be. I could be. Oh, there you go.
I'm
So
waiting
there's
for Don.
something now. Yep.
Yeah, thank you. And Donna is in near Plumas, Manitoba, and frequently well timed to be comparing to DMSP.
Yeah, wow, those look very similar to the things I showed. And what's interesting there is you can kind of see detaching green things, blobs, I guess. Is that what you're calling them?
Yeah, there was a lot of blobs. I think I was out at 7:30. Yeah, so this starts at 9:59. That doesn't make any sense. Sorry. I don't know why I have it labeled that, but oh yeah, that would be 7:59. So it starts at 8 p.m. To 9:23 is what that video is. That's not universal time, it's
Nice.
local time.
I also have a mic I was able to photograph. I put a little video together as well of, it was the first time I really noticed them, the giant undulations from Duluth, Minnesota last December. And I can show that. It's very brief if you'd like to see the video.
Sure, yeah.
All right. Thanks, Donna. Hi, Donna.
Hi, Bob.
Um, can you see, I'm trying to get the
Yep.
show up here.
Yep.
And at
Yeah,
the
those
time,
are beautiful. Yeah.
I didn't record any Steves at the time or any SARS, but this thing just went on it was during early evening, headed westward, and it went on for at least, I don't know, 40 minutes, 45 minutes with those tiny rays punctuating the undulations. So,
Yeah, nice. Yeah, and so, it'd be interesting too. I don't know whether people get so focused on looking at those things that maybe you don't look up and see that there might have been a Steve or behind you maybe.
I just let the camera, well, I usually look around, but it's possible that it may have happened like maybe earlier or something like that, but that was fairly early in the evening. So,
Yeah, and I would guess that probably it's easier to get to excite giant undulations than it is to excite a Steve. And so maybe that's why you don't see them together all the time, that just maybe during very intense events, you might see them together. Or maybe you don't see the giant undulations and, you see Steve well separated or so. But one important point, though, is, the main imaging thing in the north right now is the Themis ASI array. And none of those cameras are really, in my opinion anyway, low enough latitude to really effectively capture some of these things. And so, really a lot of the auroral photography can really augment what Themis and T-Rex can actually see. And I don't know why they didn't put something at lower latitudes, but it's sort of an uncovered region. So especially if anyone was sort of in the regions where some of those imagers were, like the T-Rex, those are clustered around, to the west of Hudson Bay, I guess. So south of there would be a really cool area, but there's imagers across Canada, I guess. So
Yeah, no, I think we are all hearing you loud and clear asking for citizen scientist contributions, I think. And that you're willing to collaborate with folks if you want to put your email in the chat, have citizen scientist
sure.
co-authors potentially, have open access papers. All those things would be great. And I want to give Margaret a chance to share as well. And we are running out of time here, but then we can go back maybe and talk a little bit more about the theory and the plasma pause, perhaps. There's a few other questions too, if you have a little bit more time, Mike.
Sure, yep.
Thanks. Margaret, please go ahead. Yeah, awesome.
Okay, I don't know if this has worked. I've never screen shared before. So did
I
that
see it.
work?
Yeah.
Okay, so that's a March 20th. Oh, no. Sorry. That one is the 7th of July, 2013. And let's see if I can do another one.
And this is from the south.
Did that turn up? Oh, gosh. Can you see another one on top of that one? Or
No, we just see the one.
it's vanished.
Something's appearing.
I have actually never screen shared before. You would never guess that, would you? Okay, let me.
It's okay. Sorry to put everybody on the spot. You're
Okay,
all
stop share.
fantastic. You're all fantastic.
Let me
You can
try
also,
again. Okay. Okay.
you can try dropping it in the chat if you like. But yeah.
Wow.
That's your screen sharing.
Whoa, yeah, that says Lee Marshall, 3 August. That's quite
So this looks a very similar thing. It's I would think those vertical pinkish things are the Steve following the peaks of a giant undulation.
Yeah, I mean, these two, we had no idea what subauroral was at that point. So we're just like,
Yeah.
what is this? Okay.
And now in the south, the motion of those giant undulations should be going to the right, whereas if you're looking in the north, they should be going to the left because they're moving sunward.
Okay, got one more. Did that work? No. Now you get to see me making faces. Okay, no, how do I get that to work? Somebody, no. Oh, wait. Did that work?
Up there. Yeah, so yep.
Yep.
Wow, those are nice.
Yeah. So all of these are Tasmania. That one's 2021. At that point, I think, we're starting to realize that subauroral was a thing. But yeah, it was a long time coming. Okay.
Nice.
For all of us. Yeah, for all of us. Yeah.
Yeah, I know it's amazing looking back through all of the photos that have been in my group over the years, and it's like, that's what that was. Anyway, super exciting.
Great. All right. So maybe, Mike, you could go back to the teardrop theory image, perhaps. And then I'm sure there are a lot more questions. I was going to ask you to perhaps describe the arrows a little bit more so that we can stare at that one and understand it a little bit more. There were questions about, so the first thing to note here is the sun is at the top of the image, the day side of the earth. We are looking at this kind of off concentric teardrop that is things happening on the dusk side of the auroral oval. And I was trying to sort of describe to Laura as like the different particles that are coming from the tail coming back towards the earth with different energies. They have different drift paths in the magnetosphere, and that kind of naturally forms these different regions and separations
Yeah,
between these regions. And I'm just saying this as sort of a preface to maybe you explaining those arrows a little bit more. Um, yeah,
yeah. So
yeah,
this is
that's a
an
good one.
example here. So this one kind of shows that same green region. And the plasma sphere, this very dense plasma sphere, is very cold. It's very not very energetic. So, in fact, a lot of times people, refer to it as zero energy, which is what I've got here, the 0 electron volt. That's just a unit of energy. And so, it turns out that even particles that have zero kinetic energy still move because of the electric and magnetic fields in the magnetosphere. So this is just examples of how these very, very, very low or zero energy particles can move. So if you start a particle out in the magnetosphere here, it can just move up there. If you start it just a little bit over here, then it actually does something funny. It goes all the way around here and then out. And out here, they would do similar things like this. There's this sort of magical, in fact, they call it the separatrix, the separator line between particles that travel these open trajectories. They come from deep in the tail and they make their way to the day side magnetosphere where they're kind of lost. They go outside the magnetosphere and then they're lost into the solar wind and you don't see them again. But there's this magic separator here where inside of this region, particles just keep circulating around. And it's the reason why this region inside here builds up in intensity is because particles from the ionosphere are constantly coming down the magnetic field lines into the magnetosphere. And so when they hit this region, they just build up. They can't go anywhere. If they hit outside this region, then they can just drift away. And so that's what causes this very dense teardrop shape like this. And it's teardrop because it's just the way the electric and magnetic fields interact, especially the electric field. There's a cross-tail electric field that goes across the whole magnetosphere, and then there's an electric field just due to the fact that the Earth is rotating. And it's that causes an asymmetry. So you get sort of a bulge in this region on the dusk side. But what that can do is, so it's interesting because you can actually lose this plasma if you change where this separator line is. If all of a sudden you move it in like this, all of a sudden you move it in, you can see this purple region is now in this region where it can flow clearly to the day side again. And so this forms things that we call drainage plumes. And so it's a way of like losing plasma out of this region. But anyway, this region in this bulge type area here is very interesting because it's a region where you can get a lot of flows going across it. And that's the sort of model that I presented here, that now these hotter particles can actually flow directly across this region. And when they flow across that region, this is really kind of like a separator between really dense and really not so dense stuff. So kind of like, the ocean versus the air. So this would be like the ocean and this would be the air. And if you have very strong flows moving across there, you can generate waves on that surface, just like you generate waves on the ocean. And so the idea here that we're speculating is that if you drive that hard enough, you can break these waves and cause little regions of these dense regions to pop out of this region, and also the hot regions from the plasmasphere to pop in. And it's these ones that go in that we're kind of thinking might be these blobby things, not the waves. The waves are probably these, but these might be the pieces of like green things that you see breaking off and coming. Ideally, it would be nice to see that they come towards the Steve emission, but we don't know if that's really what's happening. So anyway, that's kind of the model that we had here. So this subauroral region that we talk about is this green region really is sort of the boundary between where you would expect to see aurora in the normal oval. So outside of it, you kind of see aurora. So this is like where all of the streamers are and the omega bands and all the bright arc things, green and so on. If you go inside of this region, you're at lower latitudes. Remember the magnetic field lines map. So this is lower latitude, this is higher latitude. So this green kind of represents the subauroral region. So this is kind of subauroral, auroral. And so really these giant undulations are kind of like waves that develop in the boundary between those two regions in the magnetosphere. So that's why we're so interested in it, and why a lot of these different processes might happen in the same region. Steve detaching SAR arcs, the blobby things, the giant undulations, they could all be very much related to the flows, but manifesting in different ways. So anyway, that was the model we had. And we're still trying to model this numerically, and hopefully we'll get there to prove it one way or the other. Seems like the observation shows consistency, though.
Yeah, it's I think you've kind of qualitatively explained it really well. And it's still hard to explain, right? It's still hard to wrap our heads around. And so if anybody out there is like, what? Like we're all like
Yeah.
parts of it is very hard. And then when you look on the ground, from the ground, you have a different perspective, and Steve shows up in all these weird angles and the picket fence and everything. But yeah, I think Mike, did you want to share? I mean, you don't have to, but if you want to share your email address,
Oh, yeah. In the
people
chat.
I think are interested to chat with you further about different things. You know, we haven't even gotten to sawtooth events. But
Right.
yeah, you know, we'll have to have you back. This was really, really great. Um,
So
and
there,
yeah.
as a advertisement, there is one other type of thing that, yeah, if you want to do another one that hasn't really been noted by scientists for 30 or 40 years, and I bet people have observations of them. So that's a different topic, though.
A second challenge. I don't know. I feel like this
Yep.
group might be up for that. Yeah, yeah. If you want to do it quickly, if it is a quick thing.
No, I don't have it ready now, but
Oh, okay. All right.
yeah, if you wanted to do
We're
another
just
one of these.
great. Okay. We'll follow up with you on that. And Mike has his address, his email in the chat. Yeah. You could give us a preview and we could look up some things or think about it. Oh, that's a good one. That's a good one. I
Yeah,
think
there's these
you
things
have
called
that one.
fast auroral waves, and they're probably the fastest things that people have seen in the aurora, maybe, you know, aside from pulsating aurora, but there's sort of a form of pulsating, or at least they were studied by people who were studying pulsating aurora.
I
Pretty
feel
cool
like,
stuff.
go ahead, sorry.
Oh no, I'm done. Sorry.
I'm read some of the old papers on those because I worked with Tom Hallinan when I was an undergrad and on pulsating aurora as well. And then during the May event, at one point during the May event, like at 2 in the morning or something, there were some, I don't know if it was fast auroral waves, but there was like overhead of me in Washington, some just crazy striations and potentially something like that. And I think with the big storms, and I don't know if they are a big storm kind of thing. I haven't gone back to those papers, or if you have any papers that you like on those, that'd be great because they are kind of hard to,
Yeah.
they're pretty obscure.
So I think they might be related to the slamming into the equatorward region of the streamers. So it might be useful to, if you see something like a streamer, equatorward of that, you might see these fast auroral waves traveling very, very fast equatorward, like really fast, like 300 up to 1,200 kilometers a second.
Mike, I've seen those waves. They're kind of rare. I've seen them a couple times, and it was not
Hmm.
a spectacular aurora. It was in the morning hours, so after midnight, well equatorward of the main curtain, so it was overhead, and it
Okay.
was faster than I've never seen anything like it. Really, it's just a couple
Yep.
times, but it was just rapid waves, kind of rippling in effect,
Yep.
and super
And note
fast.
that Themis and T-Rex couldn't possibly see some of these faster ones, and certainly the stuff from space could never have seen these. They're just too fast. So kind of the only hope. I mean, the way they saw them in the past was or image intensified video cameras, so 30 frames a second back then.
Yeah.
That's even a bit of a stretch for, I do time lapses. That would be a stretch for me to do 30 frames a second, but
I would
it's
think
too.
they would be hard to record because they were faint, but
Yeah,
exceedingly
yeah,
fast. And I was thinking, what ISO would I even use? I just looked at them, and but I would have to
right.
go to the top of my ISO with an f1.4 lens, and I'd possibly be able to capture them. That might be doable. I wish they'd happen more often.
Yep.
Yeah,
Yeah, and they'd be
well,
really cool because I think they may have something to do with, these things slamming in and could be only really seen the equator of the aurora. So,
Yeah,
mhm.
it's a fascinating topic.